In this video, we are going to cover the concept of multiple steady states in chemical reactors, solving the energy and material balance equations for a first-order reaction in a mixed flow reactor, and we will discuss the conditions that will give rise to multiple steady states. The concept of multiple steady states is not limited to the CSTR reactors. However, it's simpler to explain the phenomenon in the first place. We will begin again from the species conservation equation at steady state that for a hypothetical A going to products reaction, the reaction is first order, and the species conservation equation is derived as such. This reduces to space-time tau to be equal to Ca0 minus Ca divided by minus R sub A for the systems with no volume change. And substituting for R sub A as K times Ca, we have this expression Ca in minus Ca divided by K times Ca. Ca in is the constant inlet concentration of species A. Ca is the concentration throughout the reactor for the mixed flow reactor. The expression above reduces to a relationship between conversion X, the space-time tau, and the reaction rate constant K. Combined together, the dependent variable conversion X as a function of independent variable space-time tau has a sigmoidal shape when K, the reaction rate constant, is really a constant. And K is a function of temperature. The temperature dependency of K is obtained through a thorough analysis of the conservation of energy. And now we're going to remember how the conservation energy evolved into a function of feed flow rates, enthalpy change of the reaction, heat exchange parameters, and the process parameters such as volumetric flow rates. The conservation of energy under steady state conditions were derived as written on the screen. We have the function expressed in terms of the flow rate, molar flow rate of species A that comes in. This was an average heat capacity we will derive later in the video. The T represents the temperature in the reactor. T sub in represents the inlet temperature. This is the reaction enthalpy, heat exchange, and the shaft work related to the impeller. Now, we are going to allow some heat exchange to take between the contents of the reactor and the environment. And that heat exchange is going to be given by an overall heat transfer coefficient, the heat transfer area, the temperature difference between the contents of the reactor, the same temperature, and a coolant temperature. So in this case, we are removing heat from the reaction environment. When we substitute this expression here, and when we assume that the shaft work is negligible in comparison to the rest of the parameters, we have a relationship that is linear with temperature here, and we have some nonlinearities in this term. Let's bring the linear terms together. This term takes the energy difference between the feed temperature and the product temperature if we had our feed stream and heat it up to the product temperature. This term takes care of the energy removed through heat transfer. And now we have the term related to the reaction. This term, FA in times X, if we go back, we have FA in minus FA is FA in times 1 minus X plus RA times V. So from this expression, we observe that FA in X is equal to minus RA times V. That's what we are going to substitute here. Minus RA times V. And this minus RA times V is, of course, from the first order assumption that we have made already, is going to be reflected as K times CA times V. K term, as we already know, has a temperature dependency in the Arrhenius form, and also our reaction enthalpy change may be a function of temperature as well. 2 points to note here, that we have terms that are constants. Now let's group them together, the constant terms. This is a constant, the multipliers are constants. This is a constant, multipliers are constants. FA in CP average with a minus in front in a parentheses times T sub in plus UAHT, meaning heat transfer area, times T sub C. These are our constants. We have linear dependent temperature terms plus FA in CP average plus U times A HT times T. Then we have K times CA let us put the temperature dependency here also. K0 times e to the minus e over RT times CA times V times minus delta H of reaction. This is equal to 0. Here what we have is a nonlinear relationship, but the terms that I have grouped here they are the heat removal or energy removal terms, while the terms I have here are the energy generation terms. Energy is generated through reaction and removed through either flow of fluids or through heat exchange. So we are going to discuss the reflection of the conservation of energy in the tau x diagram, the conversion as a function of the space-time at constant temperature is a well-behaved function, but this function can run away, that is the technical term, and exhibit ignition and extinction behavior. Ignition means that you start from a very low conversion, and as you increase the space-time, conversion increases as a natural consequence of the conservation of mass. And as the conversion increases, more energy is released that is to be absorbed by the fluid in the reactor, and the temperature starts to increase, and we start to observe conversions that are greater than their corresponding isothermal counterparts. The conversion versus tau curve for an exothermic reaction has a positive deviation from its corresponding isothermal counterpart. Now there comes a point of ignition. At this point, there is an unusual behavior that as the space-time decreases, conversion increases. We are going to discuss these eventually. But what the system does is to jump straight up to the higher conversion point and proceed there. In other words, when we have a very small increase in the space-time, a very small fluctuation, that is sufficient to ignite the reaction to almost full conversion. In the opposite direction, that if we are cooling the reactor by reducing the space-time and reducing the conversion, at the point of extinction, the system, instead of going to this irregular behavior, quenches immediately to the lowest conversion point. This phenomena can give rise to very unique behavioral patterns if done under control. But first and foremost, we have to pay attention that if we have a negative, if we have an exothermic reaction, if delta H is less than 0, the reaction heat is going to be increase the temperature within the reactor to extremes that we may encounter explosions. Runaway reactions are not desirable, especially in industry, And many of the reactions, oxidations and hydrogenations, are maintained at around 20% conversion in order to avoid runaway conditions. Runaway can be damaging both the reactants, both the contents, and also, in the extreme situations, the reactor itself. Now let's look at the energy balance in terms of its temperature dependency and the functionality. Here we have a function. Let us call it f of t to be equal to alpha t minus beta minus, we have a function g of t which is nonlinear, the generation term. Now this function f of t is going to have unique solutions. In other words, there will be only one root of this function. There will be only one temperature that is going to be valid for this function. Under which conditions? Under the conditions that the maximum value of g is going to be smaller than alpha. How do we know that? We are going to take the derivative of f with respect to t. That leaves us with alpha minus dg over dt. Here we presume that f and g are only a function of temperature, and therefore we deal with total derivatives. Now, if the maximum of this term is smaller than alpha, this whole group is going to be converging to some numerical value. It is this zone here that the solution is unique. And it is this zone here that the solution is unique. On the other hand, if we have the system, well, the uniqueness boundary, I'm sorry, it's not here. The uniqueness boundary is here. Unique solution. Between the uniqueness boundaries, however, the points of extinction and in ignition, for the same space-time, we have 1, 2, 3 values for conversion. We have 3 different conversion values. And those 3 different conversion values correspond to actually 3 different temperature values. So let us see if dg over, this is if let us write the uniqueness condition here. If alpha is greater than dg over dt max, the maximum value that this term can take, then our solution is unique. Well, if alpha is less than dg over dt, dt with capital T, our function has to satisfy 2 conditions. For the conditions of alpha being less than dg over dt max, our function has to satisfy both of these conditions in order to have multiple steady states, that the first derivative should be equal to 0 at a particular temperature, and our function should also be 0 at that particular temperature as well. Under those constraints, we have multiple steady states. Multiple steady states correspond to multiple values of conversion for the same space-time that we may encounter in a chemical reactor. This is the first situation that we are discussing this problem, but there will be other conditions, other situations that we will discuss as the course progresses.